Hi there, this video is going to talk about the common ion effect in a lot of different ways. First, we're going to talk about it when in acid-base equilibria, but then we're going to bring it back to KSP too, in the form of acid-base. So this really has all the applications of common ion when it has to deal with acid-base, since we know more about that now. So let's start. Taking a look at this here, you can see there's the Ka here, or not a Ka, but an equilibrium that has an acid, our weak acid, acetic acid. And let's say, according to Le Chatelier's principle, what happens if acetate ion is added to the solution? Well, if acetate ion is added, that's this one right here, that means this side's too heavy. Le Chatelier's principle would say there's too many products, we've got to shift it right, or sorry, we should got to shift it left to create more reactants, and that will reestablish equilibrium. Or a better way to say it in the AP world, if you add more acetate ion, suddenly your Qa is greater than your Ka, and in order to reestablish equilibrium, it will proceed to the reactant side to create more reactants and reestablish the Ka, or equilibrium. The textbook would use these words: the common ion effect. The extent of the ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with a weak electrolyte. That's a lot of words. To me, I wouldn't memorize that definition, but you go for it if it works for you. I think just applying Le Chatelier's principle, again, just this case to Ka instead of saying KSP, is a lot easier. Okay, so I'm going to take that kind of idea about having equilibrium and shifting it and that sort of thing with this problem. Here we go. Alright, so calculate the fluoride ion concentration and pH of a solution that is 0.2 molar HF and 0.1 molar HCl. Now something to notice about this is I'm trying to find the pH. Well, pH is really going to be determined by my HCl concentration. I'll get to that in the end, because HCl is a strong acid and HF is a weak acid. But the HF is going to control my fluoride concentration, so I really need to consider both when I'm looking at this problem. So I'm going to start here by writing the equilibrium expression when hydrofluoric acid goes into solution, into water. And it's going to create fluorine ions, which is something I need to solve for. Whoop, that's an H3O plus here. And I'll create my little ice table. Water's not important, so that's kind of nice. So at the beginning of time, I've got 0.2 molar HF, 0.2 molar HF, and I happen to have 0.1 molar HCl, which really means I've got 0.1 molar H and 0.1 molar Cl. The Cl really doesn't affect my equilibrium, so that's not really important, but my H is. H plus is the same as my H3O plus, so it says I'm really adding this 0.01 molar. Now I don't have any fluorine at this point in time, so here's my equilibrium, and I dumped both of these into the solution, and then things are going to shift. Now I've got more HF here, so it's going to have to shift to create some fluorine ions, because it definitely, if it doesn't have any fluorine ions, then its Ka is not where it's supposed to be. So in my shift, I'm going to lose HF, I'm going to gain some fluorines, and I'm going to gain some H pluses also. So now, if I put those in equilibrium, I've got 0.2 minus X, X here, and 0.1 plus X on this side. I'm going to put this into my Ka expression. Ka equals products, fluorine, H3O plus, over reactants, HF. There we are. I'll plug in my numbers that I know. Ka is going to be 6.8 times 10 to the negative 4. Fluorine is X. H3O plus is 0.1 plus X. You might be thinking the same thing. 0.1 is going to be greater than the X, so I'm going to assume that 0.1 is greater than X. And over here I've got 0.2 and negative X. Once again I'm going to say 0.2 is greater than X, but I think 0.1 is greater than X. It's got to be for sure. So I can say in the top part I've got 0.10 here and 0.20 here. If I plug and chug all my numbers in, I get X to equal 0.00136 molar. Alright, now my whole goal for this problem was to figure out what my fluoride ion concentration was. That's check number 1. That would be what X is, so that's this number right here. I did assume that X would be much less than 0.1, and definitely we can see that it is. If you do a check, it's a 1% error, so that's good. The other thing that I was asked to solve for is the pH of the solution. The pH is controlled by my H+. I wanted to have 0.1 plus X, so really what I'm looking at is a 0.1 solution. So thinking about the pH for that, my pH for that would be 1. Now if I wanted to add the 0.00136 I could, but it really wouldn't change my pH. Oh, I better be better. 0.1, 0.00 would give me those two proper sig figs. Okay, so I solved the problem with those things. One thing to note, and going back to Le Chatelier's principal idea, was I had this established of equilibrium, and then I added hydrogen. Well, suddenly this side is too heavy, so it's going to shift, we know, to make more HF, so that means I'll have less F- in solution over time. If I just have a solution that doesn't include any HCl, I would actually get an F- concentration to be 0.0117. That's much greater than my 0.00136. So you can see that as I added the hydrogen, it definitely shifted to make more of the reactants, the hydrofluoric acid, which decreased its solubility. Okay, so that would be that. You can see those problems really aren't much different than the ones we've done before. Sometimes you might have to add common ions and you'd put it in this change part, and that would be fine. Like if you added fluorine ions, you'd probably put it in this change part. You do 0.2, X and X, and then you put in the change part, and you come up with your ice table. In this case, they said I put this part and this part in at the same time, so I chose to do it all in the initial part. It seemed to be an easier way to go. Okay, so that would be common ion effect when you're looking at Kas. What I want to go back to is solubility, because there are really 4 factors that affect solubility. That was when we were looking at KSP. Like you have a solid, you put it into water, some of it will always dissolve. KSPs look at when you have a really small amount that dissolves. But we can create more dissolving by looking at common ion effect. We talked about that. Complex ions, we talked about that too. But the last two would be pH and amphoterism, which we haven't talked about yet. pH really isn't too tricky. Let's say you've got something like magnesium hydroxide. Well, if you wanted to put in a basic solution, suddenly you'd add a lot of base, that's a lot of OH, and the Le Chatelier's principle would say, this isn't good, we've got to shift it to create more solid, so that would mean it is less soluble in a basic solution. At the same time, thinking about bases, you can think about acids. If I took magnesium hydroxide and put it into an acid, an acidic solution, like instead of dissolving in pure water, I might dissolve it in nitric acid or something like that, then I have H pluses hanging out. H pluses are going to react with OH minuses to make water, and that will take away the OHs, so it'll continually shift to create more OH minuses, which would increase the solubility of magnesium hydroxide in the water. So pH can affect how much can actually dissolve in the solution. We're going to come back to these examples. The other thing would be amphoterism, which is just kind of a weird complex. Remember, AP doesn't expect you to know about complex ions and what they really are, but they expect you to understand that they kind of exist. And that's where these example problems I'm going to come back to will help you with. But amphoterism is the idea that sometimes you have these metal oxides and hydroxides that are soluble in a strong acid or base, because they can really do either. So like your aluminums, your zincs, and your tin, let's make this in the big screen. If you add it in an acid, it will strongly dissolve in an acid too, because it'll make this aluminum plus water will make an aluminum hydroxide solution. Okay, so the aluminum hydroxide solution will be strongly favored to produce aluminum hydroxide in a complex ion form. Now if you added in an H+, the aluminum hydroxide will dissolve in the H+ solution, because it's already been made with a complex ion, and it'll force the water to react with the hydrogen, and that'll cause more of the aluminum to actually dissolve with it. So either way you look at it, aluminum can dissolve in an acidic solution or in a basic solution. It makes these funny looking complex ions, which I showed you this picture before. So all in all, you should know that this kind of exists. Let me go to a few problems here, and hopefully that'll help. I'm going to create a new... Okay. So let's look at the problems on the left. What we're trying to decide is if you add in an acid, will it dissolve better? If you add in a base, will it dissolve better? Which one would it do? So if I look at this first one, nickel hydroxide. When I put it into water, we know that it's going to create nickel, 2+, and hydroxide ions, 1-. So clearly if I chose to put an acid into there, H+, the H+ would hook up with the OH- to make water, and then this would shift to try to remake the hydroxide that you just took away. That means that NiOH2 would be more soluble in an acidic solution. On the other account, if I tried to add OHs, adding OHs would add too much to this side, so it would shift left to create more solid. It would be less soluble in a basic solution. Okay, let's try another one. Calcium carbonate. CaCO3, put that in the water, we make calcium plus carbonate. Alright, let's add an acid first. If I add an H plus is clearly going to be attracted to a negative ion, H plus right here. H plus and CO3 will make HCO3 1 minus. Only add 1 H at a time. And we know that HCO3 is a weak acid. Since it's a weak acid, it will be formed and it will stay there, which means you have just reacted and taken away CO3. It's as if it's not there anymore because now you have it in this form. So, what does the solubility do? It shifts or dissolves more of this to create more of that carbonate. Thus, calcium carbonate is more soluble in an acidic solution. On the other account, if I wanted to add hydroxide, OH minus, to this solution, OH minus would create calcium hydroxide. If you look at your sheet, you would be like, that's a strong base. It wouldn't actually be made. But I'm going to redirect you down here. Down here we can see that it actually has a really low KSP, so that's going to make a solid. So it really is going to hook up together, create a solid, and it's as if calcium isn't here. Whoop! It's going to reshift to create more of that. It is more soluble in a hydroxide solution. Not because it's a strong base, but because it creates a solid, a KSP situation. Like I said, I'm trying to put all of these things together into one spot. Sometimes the acids and bases are just clearly acids and bases, like what's going on here. But sometimes it has to do with KSP. Alright, let's hit 2 more. Barium fluoride. BiF2 makes Ba2 plus, and fluorine 1 minus. Let's put an acid into there. Acid is going to hook up with this. H plus is going to make HF. HF we know to be a weak acid. Weak acids will actually stay together. Because they'll stay together, it's as if the fluorine isn't even there. If the fluorine isn't even there, whoop, we've got to create more of it, so it's going to create more of the aqueous ions from your solid barium fluoride. Thus, barium fluoride is more soluble in an acidic solution. On the other account, let's add OH minus. OH minus, barium, makes barium hydroxide. My world says that's a strong base. It's not going to stay together, but we do have to check our KSPs. It is a high KSP, which means it really does not stay together. It separates fully. So this won't be formed. So barium and hydroxide won't actually hook up for life and stay together, so it won't do anything. If you add a basic solution to barium fluoride, it won't make it more soluble, it won't make it less soluble, it'll do nothing at all. Alright, our last one. AgCl. Ag, Cl are solid. We get Ag plus and Cl minus. Our 2 aqueous things. Let's start with the acid side. The acid side, H plus is going to be attracted to the negative guy. Here's my H plus. To make HCl, we know that to be a strong acid, though it won't actually form. Thus, if you put AgCl in an acidic solution, it does not change how much gets dissolved. It does no effect. The other thing would be adding hydroxide, OH minus. Ag plus OH makes AgOH. Right there, that says to me, okay, that's kind of a weak base situation, but let's check its KSP. 2 times 10 to the negative 8. That's a pretty small number. But notice the AgCl, 10 to the negative 10, is much smaller. So it's going to have very few ions in solution. So few that the hydroxide won't be able to hook up to make the solid, because there won't be enough Ag and OH put together to make that KSP. Unless, let's load it with a lot of hydroxide. If we load it with a lot of hydroxide, then yes, we'll finally get a QSP that's greater than the KSP of this 10 to the negative 8, and we will make silver hydroxide solution, and it will shift to create more of that. But we've got to definitely load it with hydroxide to get over that QSP. That's going to beat out our very few silver ions on there. So I'm talking like you're going to have to load it with a lot. Very unlikely. All this information we're covering here is what we're going to be using in a lab coming up Tuesday, Wednesday, and Thursday. So we're going to get more practice in it, don't you worry. Good luck!